25. A positive 5 times a positive 5 would be a positive 25. So the square root of this negative number is undefined. It's not possible. All right, moving to number 3. Numbers 3, 4, and 5, you're being asked to approximate the value of the radical, which means you're using your calculator to determine what that number is, what the decimal is, and then you're asked to specifically round that number. So when you enter in the square root of 11 into your calculator, you'll get this very long, non-terminating, non-repeating decimal. All right, it goes on and on and on. So you're asked to round to the nearest hundredth. Now, you do need to review place value. The hundredths place, of course, is 2 spaces after the decimal point, because after the decimal point, we have the tenths and then the hundredths. So the number 1 is in the hundredths place. The number to the right of it tells me what to do with this number. So since the number to the right of 1 is 6, which is 5 or larger, I will have to round 1 up. So it rounds to 3.32. Approximate negative square root of 17 for number 4. So of course our answer is going to be automatically negative. And when you enter in the square root of 17 into your calculator, you will get this long decimal that does not terminate. It also does not repeat, but we're asked to round to the nearest hundredth. Again, make sure you remember your place value, right? The 2 is in the hundredths place. The 3 to the right of it, since it's below 5, tells me that the 2 will stay the same. So my answer rounds to a negative 4.12. And then the last one, we have approximate the cube root of 56. And when you enter in the cube root of 56 into your calculator, you get 3.825, 862, and on and on and on. And we're again rounding to the nearest hundredth. The 2 is in the hundredths place. The 5 to the right of it tells me that I must round the 2 up. So my answer rounds to 3.83. Now we're getting into simplifying rational expressions. So numbers 6, 7, and 8 are highlighted because these are the types of questions from this MyLab section that you're going to see on your MyLab test review and unit test that's coming up. So let's look at the square root of y to the 12. Now, we can take the long route, and let's just do that, just for demonstration purposes. When we have y to the 12th, of course, we're looking at 12 y's under the square root symbol. Right? So here are 12 y's, and we're trying to find the square root, which means we're trying to find 2 identical matches. That makes a square root. So I have a set here of perfect squares, so I can take out those 2. I have another set of perfect squares, take that out. Another set, take that out. Another set, take that out. Another set comes out, and a last set of perfect squares of y's comes out. So I have 1, 2, 3, 4, 5, 6. I have a y to the 6th, which is the answer to the square root of y to the 12th. Now, I could have looked at this differently. I could have used the product rule, which means when I'm multiplying like bases, I add the exponents and keep the base. So when thinking about y to the 12th, when I multiply y to the 6th times y to the 6th, that actually does equal to y to the 12th. And so these two are what? perfect squares, right? A perfect square match. So that will equal to y to the 6th, right? But just using it the long way gives you an idea of how we can use a prime factorization to extract our perfect square matches. And then moving to number 7. Find the square root of 36 over 121. Now, when we're dividing a radical, we simply take the square root of the numerator and the square root of the denominator. And it just so happens in this case that both 36 and 121 are perfect squares, right? So 36, which is 6 times 6, is a perfect square, and 121, which is 11 times 11. So the square root of 6 times 6 is 6. The square root of 11 times 11 is 11. So 6/11 is the answer. Now, we're moving into our next several questions where we want to use prime factorization to help us find the square root of numbers 8 and 9. For example, if you go back to what it means to create a factor tree, right? 20 is 2 times 10, 10 is 2 times 5. So the prime factorization of 20 is 2 times 2 times 5. But let's consider this. We're trying to find the square root of 20. So if I look at the square root of 2 times 2 times 5, then it makes it easy for me to identify my perfect square matches. So I have 2 times 2. These are perfect squares. So I take that set of 2's out. And what I mean by taking it out, I only take out a 2, which represents the perfect square that I have here. And what's left under the radical sign is a 5, because the 5 by itself is not a perfect square. So we still have the square root of 5 there. So the final answer is 2 square root of 5. And here's how you can easily check your answer. Take your calculator and find the square root of 20. Just look at the approximation of the square root of 20. And you'll find that it is 4.47 rounded. Take your answer, put in 2 times the square root of 5, and you will also see that it equals to 4.47. So that's just a quick way you can use your calculator to check to see if you are of course, simplifying correctly. Sometimes you can get a perfect approximation match, but still not have a completely simplified radical. So you have to be careful about that. Now we'll move, and let's put our answer here. Right? The square root of 20 is 2 square root of 5. All right, so now let's move to number 9. So now we have the negative square root of 500. So let's take our time and do our prime factorization for 500. And you can start with any 2 numbers that multiply to give you 500. I'm just using 5 times 100. And then, of course, I have 10 times 10. And both 10s are 2 times 5. So my prime factorization for 500 is 2 times 2, all right? I have 2 of those, and I have 3 5s, times 5 times 5 times 5. So the square root of 500 is the same as the square root of 2 times 2 times 5 times 5 times 5. Now, I want to be careful again because we're looking for perfect square matches. So I have a set of 2's that's a perfect square. I'll bring the 2 out. I have a set of 5's that are perfect matches here. All right, two 5's. So I'll bring that out and multiply it times the 2. But under the radical, I still have what's left, which is the square root of 5. So that remains under the radical sign. So my answer is 2 times 5, which is 10 square root of 5. But I'm going to do just a quick check to make sure that my answers match up. So I'm going to put in my calculator the square root of 500, which equals to 22.36. And I'm also going to put in 10 times the square root of 5, which also equals 22.36. So I'm just checking to make sure that my answer should line up with this approximation. So to simplify a negative square root of 500, that's a negative 10 square root 5. And now we're moving to number 10. Find the cube root of 162. So we're going to do the same thing here. We're going to take 162 and complete a prime factorization. So, of course, 2, I'll just start with 2. 2 times 81. 81 is 3 times, should be 27. And 27, let's make a little bit more room here. Here we go. 27 is 3 times 9. And then, of course, 9 is 3 times 3. So my prime factorization of the square root of 167 is 2 times 3 times 3 times 3 times 3. All right, I have a 2 here, and then I have those 4 3s. Let me straighten that out just a tad. There we go. Now, we are looking for the cube root. We're looking for the cube root. So that means we're not just looking for 2 identical factors. We're looking for 3 identical factors that will be a perfect cube. So, of course, I have these 3 3s, which will come out as a cube root, right? Bring out that factor of 3 that represents this perfect cube. But still under the cube root sign, I still have 2 times 3, which is 6, right? So that remains because that 2 and the 3 are not a perfect cube. So my final answer is 3 times the cube root 6. Again, so go to your calculator and make sure you're using the cube root button or cube root function key and enter in the cube root of 162. And I see that it is, and of course I'm rounding, 5.45. And I'm also going to enter in 3 times the cube root of 6. And it also gives me 5.45. So my answer for the cube root of 162 is 3 cube root 6. All right, so now we're on number 11, and we are finding the square root of 45t squared. So we're not only looking at the prime factorization of 45, we also want to list the prime factorization of t squared. So, of course, 45 is 5 times 9, and 9 is 3 times 3. So I can easily write the square root of 45 as 5 times 3 times 3. And easy enough with the t squared, of course, that's just simply t times t. So now we're back to looking for perfect square matches. So we have these 2 3s that are perfect squares, so we'll bring out a 3. We have 2 t's that are perfect squares, so we'll bring out the t. But we still have the square root of 5 that's still remaining. We have that 5 that's under the radical sign. So we leave the square root of 5 there, and our final answer is 3t square root of 5. Now, you can still check the square root of 45 along with 3 times the square root of 5. You won't be able to put the t in, but you can still make sure that your 3 times the square root of 5 matches in your calculator when you also take the square root of 45, right? In this case, it does match. And then for number 12, we have 180 x to the 6th, y to the 15th under the square root sign. So we want to make sure that we prime factor everything out. All right, so let's take our time for each of these. So let's look for 180, and again, start anywhere. You can start with 3 times 60, 9 times 20, doesn't matter. So I will use 3 times 60, and I know that 60 is 3 times 20, 20 is 4 times 5, and 4 is 2 times 2. So I have, for my square root of 180, I have 2 times 2, I have 3 times 3, and I also have a 5. And all of that multiplies to give me the 180. Now I also have x to the 6. Now think about it. How can you multiply x raised to a power that will add to give you x to the 6, right? Remember, when you're multiplying like bases, you add your exponents. So think about it. What plus what will give us 6, right? And of course, x to the third times x to the third would equal to x to the 6. So that's an easy way for me to write this as a product of perfect squares. Now let's look at y to the 15th. And I want you to think about this. We have y to the 15th. Now, there's nothing we're going to, two identical numbers we're going to be able to add that will give us 15, right? We can get close to 15, if you think about it, by using x to the 7th times x to the 7th. That would be x to the 14th. But in order for us to have an x to the 15th, we would have to multiply in another x there. And I'm not sure why I'm using x's, and I should be using y's for this one. Okay, I guess it's because I didn't put the y to the 15th here for you. There you go. So again, we can't use a y to the 7th times y to the 7th to get y to the 15th, but we can multiply an additional y into that. So this still helps us to use y to the 7th times y to the 7th times y to the 1st in order to get our y to the 15th. And we have these two, right, matches here. So those are our perfect squares that we're going to use. So let's start bringing out the perfect squares that we have. So we have perfect square set of 2's that comes out, perfect square set of 3's that comes out. The 5 is going to remain. It's not a perfect square. It's by itself. We have our perfect square of x to the third powers. That's going to come out. We have our set of y to the 7th powers. That's going to come out. But we still have a y to the 1st that will remain. So underneath our square root sign, we still have a 5 and we have a y. So now we can write that final answer. 2 times 3 is 6, x to the 3rd, y to the 7th, times the square root of 5y is our final answer. All right, so now we're going to move to the last concept to help us with the final 3 questions, and that is using rational exponents to either rewrite or transform a rational expression. And by definition, and you'll see the definition here, hopefully you can read it. When we have a to the mn, that's a raised to the m over n, that's a rational exponent, that equals to, and watch how it looks, the nth root of a to the m. You see this? You see how the denominator of the rational exponent, the denominator is now the index. The numerator of that rational, right, exponent is the exponent. So we can interchangeably rewrite an expression that has a rational exponent into a radical expression. So let's look at number 13. we have the square root of x to the third. Now, if you need to put the 2 there so that it reminds you that it's the square root, that may be helpful. So let's rewrite this as a rational exponent. So I have my m, which would be 3, and my n, which is 2. And our base here is x, so that will be x raised to the 3/2 power. See how that works? Okay, let's go to number 14. Now, number 14, we are given the rational exponent, x raised to the 1/5 power. So we're going to rewrite this. Of course, we have x as the base. Our denominator is, which is our n, right? It's our index here. So the denominator is 5, so that's the 5th root. And our numerator is our exponent. So we can simplify that. That's the same as the 5th root of x. So for number 13, I guess we would select the correct answer here, and that would be A. And for number 14, we would select the correct answer, which is A as well. Now let's do one more that's similar to number 14. And this one is not multiple choice, so we have 7 raised to the 3/2 power. All right, so we know that we have our 7 as our base, our radicand in this case. And we have our denominator, which is 2. That is our index, so that means it's the square root. And we have the numerator, which is the exponent. But again, we don't have to actually use this 2 here because the square root is just the square root. So I do want to take 7 to the 3rd power, and I want to simplify that. 7 times 7 times 7, which is 343. So this is another way of writing the square root of 343.